In this video, I'm going to continue my series on the Beaglebone by demonstrating how to use its GPIOs for both input and output applications. In previous videos, I introduced the Beaglebone and I followed this by a video on how to program it using Eclipse with a cross-platform C++ compiler. In this video, I will wire simple input and output circuits that are attached to two GPIOs, one that lights an LED and the other that receives a button input. I covered this topic before in a previous video about a year ago, but I am updating it because there have been significant changes to the Linux kernel that make my previous video dated. This video will cover the Linux device tree for ARM embedded systems and explain how you can create custom device tree overlays to configure the GPIOs for your application at runtime from within the Linux user space. I will explain the use of internal and external pull-up and pull-down resistors, and I will make available and describe a set of C++ code examples for reading and writing to the Beaglebone's GPIOs. I have also built a set of PDF tables that aggregate the information that you need and make it easier to configure GPIOs on your Beaglebone's P8 and P9 headers. I make all of this information available on my website at the address that is linked here. GPIO stands for General Purpose Input-Output, and the Beaglebone has 4 banks of 32 GPIOs, some of which are already allocated though, for example to the onboard LEDs. Only around 66 GPIOs are accessible from the 2 expansion headers. This is because the pins on the Beaglebone are multiplexed, meaning that one of the outputs on the P9 or P8 header can have several different modes. I will demonstrate how we can switch between these modes and will outline which pins are already allocated and not readily available to be used. Very importantly, GPIOs on the Beaglebone are 3.3 volts tolerant pins, and unlike a board like the Arduino, they should only source or sink very small currents. It's about 4 to 6 milliamps on output and about 8 milliamps on input. You can use voltage dividers to set an appropriate level, but remember that this matters even if you are sending data between two microcontrollers. For example, if you're using the I2C bus between a 3.3 volt tolerant controller and a 5 volt tolerant controller, you will need a bidirectional logic level converter. There's a great little board available for this task from SparkFun, but just be careful with voltage and current levels. For example, in my example that I'm going to show here, I will use a transistor to protect the GPIO in switching on and off an LED, which typically has forward currents of about 20 to 30 milliamps. All of the GPIOs can be configured as inputs or outputs, which I will also do in this video. Previously we did this using an OMAP MUX that was part of the Beaglebone distribution. However, since the 3.7 Linux kernel, that is no longer available. As the Beaglebone Black comes with the 3.8 kernel, this is an issue that's quite relevant. The new kernel gives the Beaglebone access to the Direct Rendering Manager, which is required for the new HDMI video output features. So why was the structure changed? Well, thanks to the popularity of ARM-based microprocessors and controllers, Linus Torvalds was unhappy with the amount of code that was being added to Linux to describe each feature for each and every ARM device. Despite the fact that there are many types of desktop PC configurations, for example, this is not a problem, as they typically have a system BIOS, which unifies the way that the hardware is presented to the operating system. This is not the case with devices like the Beaglebone. In fact, they don't even have a battery to retain the time, meaning that we need to set the date and time each time we boot, as I have discussed previously in my blog. So what we have on the Beaglebone and Beaglebone Black now is a device tree to do this job. The device tree is described by devicetree.org as a data structure for describing hardware. Rather than hard coding every detail of a device into an operating system, many aspects of the hardware can be described in a data structure that is passed to the operating system at boot time. The device tree is used both by open firmware and in the standalone flattened device tree FDT form. This is what a device tree description of our Beaglebone Black looks like. It's a DTS format file. We have tools on our Beaglebone already to support us, such as a device tree compiler, which we call DTC, that converts between human readable and editable device tree source, which is .dts format, and the compact device tree blob, DTB representation, which is usable by the kernel. See scripts/DTC in the kernel source directory for details on the tools. The /boot directory on the Beaglebone contains the compiled DTB files that describe the hardware on your Beaglebone. If you're interested in seeing the source for these, you can see the device tree directory of the source code in my GitHub repository to support this video. We can actually build our own device tree description of the Beaglebone and replace the description in /boot. However, there is a much better way to do this at runtime from user space using device tree overlays. The alternative would mean that we would have to reboot every time we change the device tree. So that's what I'm going to do here. I'm going to use overlays in this video. If you were designing your own cape for the Beaglebone, you would go through a similar process. I've used the information in the Beaglebone SRM to create two tables that bring together all of the data you need for working with the GPIOs. Here you can see I have highlighted in red any pin that is in use in the default Beaglebone configuration. You can find this information too by reading the SRM and the Beaglebone schematic in detail, but hopefully you will find this information useful. And please notify me if you notice any mistakes. I had to rekey data at times, so it is possible that there are mistakes. Here's my circuit configuration for the LED and for the button. For the LED, I'm driving this through the 5-volt rail from the Beaglebone. This is the red line is 5 volts. That's coming to the positive side of the LED. The negative side of the LED is going through a 100 ohm resistor, and it's going to the transistor, into the collector pin of the transistor. That's fine, because if you look at the line that's driving the transistor through the base of the transistor through a 10k resistor, I'm driving this using P912, which is GPIO 60, and a very, very small current driven through into the base of the transistor will effectively switch the transistor on. The emitter of the transistor is then connected to ground. So that's the LED circuit. For the button circuit, I have my 3.3 volt supply coming from my Beaglebone. That's going to one pin. I'm using a pull down configuration for the input, which is, you should be very careful with pull down that you don't short or you don't use the wrong supply. But here I'm using a pull down configuration, so the pin is currently pulled down. I'm using no internal pull down, pull up resistors. So this is purely an external circuit. You can see that there's a 10k resistor pulling this to ground, and this is the ground is going back into pin 45 of my Beaglebone header, and then I'm using just a 100 ohm resistor just to be sure to protect the pin, and this is going to pin P924, which is GPIO 15. So effectively, when the switch is open, as it is now, it's a normally open push button switch, you can see that this line is grounded through these two resistors to ground. However, when I press the button, this is going to short across these 2 points, which means that my point here is connected to my 3.3 volt line via the 100 ohm resistor. So that's my circuit there for the button. The other three over here, 3 outputs here, I'm going to use these in a second. These are my P8 header, and this is P8 11, 12 and 13, and they're the pins that I set up within the device tree overlay. In using the Beaglebone, there are a few documents that are particularly important. Probably the most important is the Beaglebone Black System Reference Manual, or SRM. This is the document that contains much of the information you need in order to get started with the Beaglebone and work with the GPIOs and so on. You can see that down towards the end we have lists of all of the pins, particularly the P8 header and the P9 header are listed as tables within the document, and they're quite complete tables. There's also another table at the end now for the Beaglebone Black, which lists all of the EEPROM pin usage, the connector name and the offset. I have created a new set of tables that integrate the information with the P8 and P9 header and this table and some other information as well to try and make it easier for working with the P8 and P9 headers. The other documents that are important are the schematic, because certain pins are already used on the Beaglebone before you start using it. So you can see if you go down, for example, let me see, here's a set of pins that sysboot 0. These are LCD data 0 through to 15, and you can see that there's already resistors, external resistors on both sides of the pins. So it's important that you're aware what's actually happening in the hardware, sort of not inside the controller, the microcontroller, but outside on the circuit board. The other document that's very important is the technical reference manual, TRM, and this is the AM335X. So this is for the microprocessor itself, and it has loads of useful information. Some of it this is a very long document. It's probably 4,000, is it? How many pages? Over 4,000 pages in length. And for example, if we go in here into section control module registers, we can go down and let me see, I'm looking for 3.51, and you can see here's a very important table. This is the table that's important for this video. This is on section 9.3.51, page 815 of the TRM. This is the control module register setup. So this is control module pin register field descriptors. And you can see here, this is the way that we describe the mode of a pin and whether we're using pull-up, pull-down resistors, and so on. So you can see here, the last three bits 2, 1, and 0, define the MUX mode. So this would be a number between 0 and 7. And you can see in a minute that all of the GPIOs are actually 7. So we use a 7 there to specify that we want to enable a GPIO on that pin. The next thing we have is if we want to pull up or pull down a resistor, whether they're enabled. So that's if whichever one we select here. So on bit 4, we select whether we want pull up or pull down, and on bit 3, we specify whether we want it to be enabled. So for example, if we wanted to enable pin 7, we would have 111, mode 7, for mode, and they would be the least significant bits. And then we would have a 0 to say we wanted to enable, and let's say it was pull up selected. So it would be 1, 0, 1, 1, 1. If we wanted to be an input or output, we can enable receiver enabled or disabled. And the slew rate, I haven't really seen this in action yet in terms of its use, but it can be either fast or slow. So you can see that this is a very large document, but there's some very important information embedded within it. So the two tables that I've created are one for the P9 header and one for the P8 header. And effectively what I've tried to do is integrate some of the information that is in the SRM alongside information about the hardware. So for example, over here I've got the notes. For example, the maximum on DC 3.3 volts is 250 milliamps max. DC 5 volts, 1 amp max, depending on only if it's DC power jack, and so on. But here's the important thing. We have the header pin. So this is P9, pin 14, or pin 11, 12, 13, 14 on the P9 header down to pin 46. Pins is the software pin label that's placed in that. We'll see that shortly. The address is the actual address. So it's 44E10870 is the address of pin 28, which is P9, pin 11 on the P9 header. You can see that the name for this is UART4 or XD, and it's GPIO 030. And 030, 0 times 32 plus 30 is 30. The next one, GPIO 128, 1 times 32 plus 28 is 60, so it's GPIO 60. So mode 7 is the GPIO mode. Mode 6, mode 5, there's only one with mode 5, 4, 3, 2, 1, and mode 0. So these are the different functions that you can have associated with each one of these pins on the P9 header. I've highlighted some of these in red, 94, 95, or sorry, this is P9, 19, 20, and so on. And the reason is because these are already allocated. For example, 95 and 94 are pins 19 and 20 on the P9 header. These are already allocated to the group PinMux I2C2. So the I2C bus, the second I2C bus, they're already allocated, and so on down. You can see here, for example, these are allocated to MASP0. So the final pin here, this is the actual pin on the processor, and the reason for that is if you want to relate that back to the TRM, you can see the pin on the processor and so on there. There's an equivalent document for the P8 header. So this is the P8 header, and you can see as well, you can see quite a number of these pins are already allocated to HDMI. So if you're using the HDMI Output, you're going to need to leave these pins alone, pins 56 through to 40, P27 to P46. You can also see that we have other ones here used for the eMMC, and other pins up here used for the pin eMMC2 as well. So quite a number of these pins are used, and you can see the effect of that is when you start to enable them that something else mightn't work correctly, or your board mightn't boot if you have an external circuit wired and so on. So you have to be careful with those pins. Further reading is required effectively when you see a pin in red. The GPIO settings are down here, and I've just transferred this here. So in 2 pages I've tried to capture as much information as possible. The offset, we're going to need that shortly. So again, let's look at say this one, P808. That's pin 8 on the P8 header. Its software pin 37. Its actual address is 44E10,894. So its offset is 094 from E10800, which is the first pin, pin 1. The GPIO number for that pin is 67, and it's GPIO 3, so it's 2 times 32 plus 3. 2 times 32 is 64 plus 3 is 67, and you can see here it's not allocated, so it's available to be used. So first things first, I'm going to SSH into my Beaglebone. I've set up a static IP address on my Beaglebone, .80. I've explained how to do that in my blog. Log in as root. Okay, and here's my directory. So I have nothing in here, just a backup directory in my desktop directory. You'll see that, let's say, I have Linux 3.8.13, which is the recent distribution to the Beaglebone Black. You'll also see that the date and time are working directly from boot, and the reason for that is because I've set that up on my blog as well, so you can see that there. The first thing that we're going to do is we're going to download the source code for the example. So I'm going to use git clone git. You can use git :// This is probably easier. I just want to show you that HTTPS is working too. I have that set up. I explain how to do that again on my blog. It's useful if you're writing to repositories more so than reading from them. This one is called bone device tree.git. So clone into bone device tree. Okay, now we have a directory bone device tree, so we can go in here. And you can see that we'll have a number of directories. We have a directory for overlay, which is what I'm going to work on here now. GPIO, which is the C++ code. DT source is the actual source code for the Beaglebone device tree for Linux 3.8.11. I'll put one up there for 3.8.13 as well. Okay. So if we just go back to our root directory, I'm just going to set up a couple of environment variables before we get started. Now, I've actually set them up in my .profile, but just to show you the values, export slots is the first one we need. And this is going to be /sys/devices. I'm just going to use autocomplete by hitting tab and bone catemanager.9/slots. And you'll see the slots file there. Okay, we also want to export pins, and this is going to be equal to /sys kernel /debug pin control, and it's a long number here, 44E10800.pinmux. That address is very important. You'll see it appear loads of times. That's our base address, and everything we're working on is offset from that. And we've pins. So there are 2 environment variables that we need. You'll see that I've actually set them in my .profile as well. So you can see that they're the values that we've set. That's the way that I've set the curl up for SSH. And then here's my 2 environment variables as well. So a better way of doing this is to have them as part of your profile so that they're there every time you log in. If we wanted to execute the profile again, we could say /tilde/.profile. And that would do the same, have the same effect in this case. Now, Okay, we can check that these values are fine. We can echo slots to see that they're set up right, and echo pins. Okay, and that gives us that. We can then do we can cat the slots so that we can actually see what's there at the moment. So at the moment 0, 1, 2 and 3 are free and are available for capes to be added to your Beaglebone Black. We also have 4 and 5, which is one is the eMMC, the way that where we store our data, and the HDMI. So we want to create a virtual one, number 6. So we'll do that very shortly. And we can also cat the pins to see what pins are present. I'll put in a pipe more, so we can see these are all our pins, registered pins, 142, pin 0 through to 141. And you can see each one of these are our pin 0, that's our base address, that 44E10800 is very important. We can see its mode is type is 31, and its pin control single. And so on down, you can see there's 27s and 17s and 37s, and we'll see why that's important. This is the pin that I talk about in the document, in the PDF document, as being $pins, because just to make it clear that there is a mapping. This is not GPIO 0, 1, 2, 3. These are pins 1 to 142. I'm not sure what these actually mean, but there's no direct relationship between that and the GPIOs. And you can see there's the 141 of those pins. What's useful about this is that we're going to be able to actually see that the modes have changed. Okay, so back into where are we now? We're in this bone device tree. So let's next go into our overlay directory, and this is where I have the code to describe what we want to happen. Okay, so I'm going to moor the overlay. So here's my device tree overlay, and you can see that if we look at it, you can see it's based on the example that comes from Texas Instruments. There's more information on this particular example at github.com, Jaden K, validation scripts, blob, master, test cake manager. So I've modified this for my particular GPIOs, and I've just made a few minor changes and tweaks to the naming and so on. So the actual overlay itself, you can see that it's compatible with the Beaglebone. I've set it up so it's compatible with the Beaglebone and Beaglebone Black. Its part number is DM GPIO test, and you'll see that'll appear. I'm using version 00A0, which is in line with the other devices within firmware. And here's the first fragment, fragment 0. So the target is the AM33XX pinmux, which you can see elsewhere. Pin control test, DM GPIO test pins. So here are the pins that I'm going to activate or set their mode according to what I want to do. So the first thing we need is the offset address. So this is the offset address for the pin P912, so pin 12 on the P9 header. This is GPIO 60, which you can find from my table. And you'll see that the offset from 800 is 078. So the absolute address is going to be 878. And we want this to be in 07 mode. So that means that we have all the flags are set to 0 with the exception of the last 3 bits. And that means that we're activating this as a GPIO. We're using this as our LED output, and this is in mode 7. The other 4 are all inputs, and we want them in mode 7 again as GPIOs. And what I've done here is I have a combination of internal pull-up, pull-down resistors and none. So in the case of the button itself, this is pin 24 on the P9 header, and this is at address 184. This is the offset address, and we want this to be in mode 2F. So you can see here 2F, anything F here as an output means no pull down or pull up resistor enabled, internal pull up or pull down resistor. And as a result, my circuit needed the external pull down resistor. So the next one, I've then, just for test purposes, I've just enabled 3 other pins, and these pins are P8, 11, 12 and 13. So pins 11, 12 and 13 on the P8 header, and these map to GPIOs 45, 44 and 23, and I'm putting them into different modes. So you can see that this is the offset that you can get from my table, and in this one here we want this in mode 37 hexadecimal, and mode 37 says it's in pull up configuration. So here we go, and it's output. You can see it's pull up configuration, so it's going to be 0110111, and that means it's in pull-up configuration, and I'm going to show exactly what that means. And the yellow wire then is in pull-up. So the remaining wires, the green wire is going to be connected to pin 12 on the P8 header, and it's going to be in pull-down configuration. And finally the white wire, which I don't really use, but it's there anyway, is going to be in neither pull-up or pull-down enabled. And this is pin 13 on the P8 header, but I'm just going to measure the voltage anyway shortly, just to show how it behaves. So this is in 2F mode, which means no pull up or pull down. I've just put the question mark in here because it doesn't really matter whether you enable it for pull up or pull down. If you don't, or where you set it for pull up or pull down, if you don't enable it, it doesn't matter. So that's the point. The rest of this file, then we've got our second fragment, which maps this pin control test. So you'll see here, pin control test has been mapped, and you can see that this is, we're using the Bone PinMux helper for this, and status OK is the way that we enable it. So that's our device tree overlay. We can compile this now. To make life easy, I've built a build script here, so more build, just so you can see. Slightly unusual notation, because you say you're calling the device tree compiler. The output format is DTB. It's going to be one of these blobs, binary blobs. -O is the output file name, is DTB0, so this is the output file name. And the very last value you pass in is actually the source. So this is your source file that we just viewed a second ago. So to compile this, we can just do /build, and we end up with a file in our directory called dm GPIO test 00a0.dtb0bo. So we can copy this now to dm, copy this file to /lib/firmware. Okay, and then we can go into /lib/firmware. I'll just do an ls, and you can see here dm GPIO test 00a0 is here in our firmware directory. So let's go cat pins, and we're going to search for the offset address, grep, actually the full address of each pin. So the full address of P912 is going to be 78 plus 800, 878. Okay, so that's in pin mode 37. We'll do the same, we'll search for the next one, which is 984, 834. Keep going, 834, the next one was 830, I think. Next one was 824. So you can see here that at the moment, the first two were mode 37, 37, 27, 27, 27. So on the P9 header, the two pins were mode 37. And on the P8 header, the three pins were mode 27. So what we're going to do now is we're actually going to apply, and if we echo slots again, or cat slots rather, slots, you'll see again we had our 4 gaps and our 2 descriptors. So let's apply our firmware. So we echo dm GPIO test, and we get rid of the extension and the version number. We echo that directly to slots, and we end up with no response. But we can see if we cat slots again. Now we've got a difference. You can see that it says on slot 6 we've got override board, version is 00A0, override manufacturer is DM GPIO test. So that has now been applied. Let's have a look at the pins now. So if we go back, the first pin was 878. Okay, the next pin was 894. Next pin was 834. The next one was 830. And the last one was 824. And you can see now that we have our new settings. So on pin 30, which is our LED pin, it's now set for mode 7. Our button on our P9 header is set for 2F. And we have 37, 27 and 2F as the MUX mode for our 3 GPIOs on the P8 header. So that's all set up. We can also use dmesg, DMESG, to see what the output was when we applied this cape, and you can see here And there's our effect. Part number, DM, GPIO test, version not applicable. Generic override using board EEPROM data slot 6. Override board name, and you can see it goes on. I applied 2 overlays and there's no errors there at all. So everything looks good. So that means now that we've applied this overlay, it's described here, and all of our pins now have the correct modes. We can now go to our GPIO location. Let's go to sys class GPIO, and you can see here's our 4 banks of 32 GPIOs. We can export these now directly, so we can say, for example, let's use the LED one. Let's export that. So we can go echo, and the LED is GPIO 60. So echo 60 to export. Now if we go ls-al, we now see we have GPIO 60 directory. So we can go into GPIO 60. And we can see that we have information here that we can examine. Let's look at the direction. It's an input pin. Well, let's change that to output. So now we've set it up as an output pin. And currently the LED is off. And if I go echo 1 to value, the LED has just come on. I can echo 0 to value, and the LED is now off. So that's the way that we now have to write code shortly that will do the same thing as we're doing here at the command line to export the pin, set the direction, and set the value. And that's the way that we're able now to set a 1 or a 0 to our GPIO. Okay, so now I'm going to export P924, which is GPIO 15, and this is from my push button switch. So I'm going to echo 15 to export, and you can see that we now have GPIO 15 directory. And we can cat the direction. We see it's an input, that's the way we want it. And we can see that the value is 0. So we'll do it a few times just to give ourselves some space, so it's consistently 0. So now if I press the button and hold the button, you see we get a 1. Let go of the button again, and then we get 0 again. So you can see my button is working correctly, and again we have to mirror this functionality so that we're able to detect that the button has a state of 0 or 1 within our C++ code. If we go back a little bit, we can see that we can now unexport these values as well. So we can go echo 15 to unexport, and echo 60 to unexport. And effectively what we're doing when we import or we export a pin, we're exporting it to user space. Unexporting makes it available within, I suppose, within kernel space. But once we export it, we have access to it in user space. If you need to find out information about the pins, and indeed we dealt with this already through the pins environment variable, so if we actually echo pins, you can see that we're working in syskernel debug pin control. So we can go there, syskernel debug pin control 44. And you'll see there's a few different files here that we can get information from. For example, and this is the way that I generated the PDFs, if we want to find out, for example, cat pin mux, let me see, pins, more, we can see which pins are claimed and unclaimed. So here you can see pins 0 through to 7 are claimed and allocated to EMMC2, and you can see that many of the GPIO pins are unclaimed there. We can also get a different view of that if we go cat the pin groups. Maybe do a pipe more. You can see here are the pins 21, 22, 23 and 24 with the addresses are allocated to user LEDs, and so on I2C0, I2C2, and all the addresses associated with that. So there's plenty of information there in that directory, syskernel debug pin control and the 44 pin mux. Okay, so I'm in my GPIO directory, which is where I have my C++ code. So we can see I have my test application.cpp. So we're going to build this, and we're just going to go g++ minus o2 minus wall. This is just to give the proper level of errors and optimization, which is, I suppose, unnecessary this time. And it just compiles the two CPP files and outputs our test application. So /build goes off and builds. So now we end up with our test application. So we can just execute this directly. So here I have, and you should see it should flash the LED. And maybe just look at the code for a second. It's linked to GPIO 60 and GPIO 15. Okay, so it's going to flash the LED 5 times and then wait for us to press a button. /test application. So you should see the LED flash 5 times, and then it's printing dots until I press the button, and I'm just about to press the button now. And you see, as soon as I press the button, it pops up a message to say button was just pressed, finish testing GPIO pins. Execute it again, LED flashes. This time I'm going to press it an awful lot sooner. So that's working. So we have output to our LED, and we have button press as an input. So just to run through the code that's there very quickly, there's a simple header file, simple GPIO.h, and its associated CPP file, and also the test application.cpp. So the simple GPIO.h and CPP file are the same ones that I've used before. If you just look at it, the .h file, the header file, you can see it's based on the work by Ridgerun from last year, and it's what I used before in the video before. There's a couple of different functions defined. Export, to export the pin, to do the same as what we had to do when we passed the pin number, GPIO number, to the export. So we do the same thing. Unexport, set the direction, set the value, get the value, set the edge, and then two helper functions, open and close. We also have two enumerations, one for the input pin and one for the low or high value. So they're just standard functions. So this is a nice wrapper for the file operations that are taking place. The actual application itself, the test application, CPP, it's not very sophisticated. You'll see here it includes the simple GPIO.h header, also IOStream, string, and we're using unistd.h for the time function below, just to wait for a certain amount of time. The LED GPIO is declared as pin 60, as GPIO 60, and the button GPIO is pin 15. So we go into our main function, print out a message, and you can see it prints out testing the GPIO pins. We export the LED pin, we export the button pin, we set the direction of the LED pin as an output pin, the button pin as an input pin. We flash the LED 5 times by setting the GPIO set value high, sleep, this is microseconds, so microseconds, this is micro is just before milli, so 200 milliseconds, and we print out messages for ourselves, but that's not important. Then we set the LED to low, and we sleep for another 200 milliseconds. So it's going to come on for 200 milliseconds, off for 200 milliseconds, and loop around that 5 times. Then it offers the option to press the button, and all we're doing is carrying out a do while. So continue to do the following operation while the value is not equal to high. So this is assuming that the button is its normally open condition is low, and when you press the button you're triggering a high. So all we're doing here is getting the value, printing out a dot. If we sleep for 1,000 milliseconds, or sorry, 1,000 microseconds, which is 1 millisecond, and we continue until the value is high, and then button was just pressed. Finally, we print out that we're finished, and we unexport the LED and button GPIO pins. So what you'll see here is that they disappear from the directory as if we had unexported them from the command line. So that's a simple application. It's not very sophisticated. It's not using interrupts. It's It's a very basic polling that's taking place, and there are better ways to do this, but this will get you started. Okay, so you'll recall that I had 3 extra outputs, or well, 3 extra wires that are inputs into my Beaglebone that I'm using as GPIOs. And I just want to use the voltmeter just to show you the effect of setting mode 37, 27 and 2F, for example. So we know that, for example, from previously, that the yellow wire here is connected to P8 pin 11, and this is in pull-up configurations, mode 7 pull-up configuration, and that is 0 by 37 hexadecimal. The green wire is in pull-down configuration, and that's because we passed in a value of 0 by 27 hexadecimal, and the white wire is again in mode 7, but we have disabled internal pull-up and pull-down resistors. So again, yellow is internal pull-up, green is internal pull-down, and white is none. So let's look at the effect of this on the when we measure the voltage. So you can see that I connect the black probe to the ground, and I measured the first one first, so the yellow pin first of all. And you can see that when I measure this, again, this is in pull-up configuration, so the pin has been pulled up to the 3.3 volt rail, so it's close to that. It's 3.166 volts, so you can see that that's in pull-up configuration. P812, the green wire is pulled down, internal pull down. Again, there's nothing else connected here except for the wire. So you can see that when I connect that, you can see we're at about 1.2 millivolts. So that's very close to ground. And that's in pull down configuration. And finally, the white wire has no internal connections, so no internal pull up or pull down connections. So if we measure the voltage in that, just get a bit of the metal visible. Just do this at a distance. So you can see that at this we're getting 0.445 volts. So this is effectively floating as an input. So we would need external pull-up or pull-down resistors to drive correct voltages levels with this pin. So I'm going to concentrate on the first two first. So again, yellow, which is in pull-up. So it has a value of around 3.3 volts. So if we wanted to connect this as a switch, it's very easy. We can say use the blue button here. So push it in, and now it's home, it should be home. And I'm going to use, so it's in pull-up configuration, so we're going to ground this other side of this pin to our ground out. The green one is in pull-down configuration, so I'm going to use another button. Okay, push it in, it's not sitting very well. And I'm going to connect this into my 3.3 volt rail over here. Okay, so now I've got 2 new buttons connected, and the blue button now is going to be connected to GPIO 45, and the red button is connected to GPIO 44. So I can go over to my shell here, and I can go in and say, well, let's echo the 40. Which one's first? 45. The blue button to export, and echo 44 to export. So let's go GPIO 45 for the blue button, and we can check the direction, and it's an input, which is what we want, so we can cap the value. And you can see that the value here for the blue button, because remember the voltage was at 3 point something volts, the value is naturally high in this particular case. But if I press the button, so just press the button and hold it, you can see that the value is now low. Release it, press it again, and you can see that we're getting a 1. So effectively pressing the button returns a 0 in this case. Leaving the button depressed, it gives us a 1. Okay, now if we want to check the red button, we see this is GPIO 44. Go into this directory, just check the direction. You can see it's input, which is good. And if we cap the value, we should get the opposite. Yeah, it's setting a value of 0. So in this case here, it gives a constant value of 0. And in this case, if I press the red button, you'll notice that the value now is 1. Release the red button, at the value of 0. So it does exactly the opposite in that case. So hopefully that has helped you to understand the effect. I didn't bother with the white one because I've already done that over here. with this button, you can see here's the use of the external pull down resistor, or you could have an external pull up resistor and do the same thing. One thing that is recommended by some people is to use a 100 ohm resistor on the input pin. It's probably a good idea to use a 100 resistor, 100 ohm resistor between the green line and the button, just to protect the circuit. So that's it for this video. Hopefully you now have a handle on how to use device tree overlays for integrating with the GPIOs. It's possible that in the future this will get easier, but for the moment, for the near term anyway, hopefully this will get you started.